Welcome to lesson 2 of 3 in this tutorial, Mass Number and Isotopes. Last time, we looked at fundamental particles and the basic structure of an atom. Now, we'll be focusing our attention on mass number and isotopes. Last time, we looked quite closely at how the nucleus works and the structure of electrons around the nucleus. Here's a list of key learning objectives we'll be covering in this session. We'll start off by looking at atomic and mass number, and then we'll move on to looking at defining isotopes, and finally we will look at the process of mass spectrometry. We're now going to look at two very important concepts. These are atomic number and mass number. This is the atomic number. As shown here, this is the number of protons in the nucleus. The atomic number will help you to recognise exactly which element you're looking at. This is why it is said to be characteristic of the element. The mass number is the total number of protons and neutrons in the nucleus. As we discussed in the last video, we know that electrons have a negligible mass. This means that they're not usually included in the mass number. It's useful to know what the nuclear symbols are for different elements. We've just seen why atomic numbers and mass numbers are important. They're both found here and here, next to the element symbol. When we are going through this tutorial, try to make a note of and learn the different definitions that we come across. This will help you when we are trying to calculate the mass number and the atomic number in case you forget. We can perform calculations to determine the number of subatomic particles. In this case, we can see that the mass number is the number of protons plus the number of neutrons. The atomic number is different in the fact that it is simply the number of protons that an element contains. The number of neutrons is the mass number minus the atomic number. We know this since the mass number is the protons and neutrons, whilst the atomic number is just the protons. In order to work out the number of neutrons, we simply have to work out the mass number minus the atomic number. We can also work out the number of electrons in an atom, since they will be equal to the number of protons. Since the electrons will be negatively charged and the protons will be positively charged. In an atom, we must note that they're equal since the overall charge of the element will be 0 or uncharged. Here, we can see an example of an atom. This is a particle without any electric charge. In this instance, the number of protons is equal to the number of electrons. An ion is a particle with an electric charge. A particle can be an atom or a group of atoms. Ions can be positive or negative. Here, we can see that the atom has lost an electron. This has formed a positive ion, also known as a cation. Alternatively, atoms can also gain electrons. This will form an anion, which is also called a negatively charged ion. When electrons are transferred from one element to another, ions will be formed. The element that loses an ion will become positively charged and called a cation, whilst the one that has gained an electron will become negatively charged and is called an anion. As we've just seen, there are two types of ions we can form. These are cations or anions. Once again, we'll be revisiting the definitions of cations. The cation is a positive ion that is formed when an atom has lost electrons. Here, we can see a sodium atom, which has become a sodium cation. This will contain less electrons than protons. An anion is formed when an atom has gained electrons. Here we can see that the chlorine atom has gained an electron, making it into a negative chloride anion. In this instance, the chloride ion has got more electrons than protons. In the transfer of an electron from sodium to chlorine, sodium will become a positive Na cation as it loses an electron. Chlorine will become a negative chloride anion as it gains an electron. We're now going to look at the whole transfer of an electron from sodium to chlorine. We can see here that the electron is being lost from the sodium atom and gained by the chlorine atom. This results in the sodium becoming a positive sodium cation. This is because it is losing an electron. Here, we can see that it has a charge of +1. We can also see that the chlorine has become a chloride anion. This happens because the chlorine atom has gained an electron. Overall, we can see that the sodium has become a positively charged cation, whilst the chlorine has become a negatively charged anion. When doing calculations involving ions, you need to remember that the number of electrons does not always equal the number of protons. However, the atomic and mass numbers will stay the same. We'll look at the following example to help us make sense of this. In this example, we'll be looking at the formation of a calcium ion. Let's fill in the table. For a calcium atom, the atomic number would be 20. The mass number would be 40, meaning that the number of protons must be 20, and since the number of electrons should equal the number of protons, this would also be 20. The number of neutrons will also be 20. Now, we'll fill in the exact same data for the bottom line, which is a calcium ion. The atomic number will be 20, and the mass number will stay as 40. The number of protons will also remain the same, at 20. However, the number of electrons will be changed and go down to 18. The number of neutrons will also stay as 20. Here, when we compare the two sets of data, we can see that the calcium ion will have the same number of protons and neutrons. The most important thing to note is that the number of electrons will be different. This is because the calcium anion will have 2 less electrons than the calcium atom. The atomic number is the only number that will stay constant between ions of the same element. The mass number can change. If 2 elements have different atomic numbers, then they are no longer the same element. We'll now move on to looking at isotopes. The definition of an isotope is that atoms of the same element will have different numbers of neutrons. They will have the same number of protons and electrons. There are some key things you need to know about isotopes. They will have different mass numbers, since the mass number will depend on the number of neutrons. But they will still have the same atomic numbers, since the number of protons will remain the same. We'll now be looking at some examples of isotopes using hydrogen. Don't worry, you don't need to memorise these for the exam. They're just here to help you understand the topic. Here, we can see the isotope of hydrogen called protium. Our second isotope of hydrogen is deuterium, which has 2 neutrons. Our final and third example of hydrogen isotopes is one with 3 neutrons. Here, we can see that although the number of protons has remained the same, the number of neutrons have increased. The physical properties of isotopes can vary. Several physical properties are determined by mass. These can include density, boiling point, and melting point. The chemical properties of isotopes are pretty similar. These are determined by the number and the arrangement of electrons, which do not actually change. Here we'll compare the 2 isotopes of chlorine-35 and chlorine-37. Let's look at the atomic numbers of chlorine-35. This would be 17. The mass number would be 35. The proton number would be 17, and so would the electron number. The number of neutrons would be 18. Now let's look at chlorine-37. Here, the atomic number would be 17 again. The mass number would be 37. The proton number would be 17, as would the electron number. However, the number of neutrons would go up to 20. When we compare the 2, we can see that the number of protons and electrons are the same, but the number of neutrons is different. This means that the mass number will be different. However, they are both still the same element, so they have the same atomic number. Just like with ions, the atomic number is always the same between isotopes of the same element. Only the mass number will vary, and electrons if one is the ion. Now let's look at mass spectrometry. These are instruments which are able to measure relative masses. Here, we can see that we can measure the relative molecular mass, the relative atomic mass, and the relative isotopic abundance. The mass spectrometer that we will focus on for AQA is a simple time-of-flight mass spectrometer. This is very dependent on the time taken for a molecule to travel through the machine. There are 4 main events that occur when a sample enters a time-of-flight spectrometer: ionization, acceleration, ion drift, and detection. We'll look at each of these in turn. Before we begin, the sample must be vaporized into a gas form. This is shown here. Then, the sample is put into the mass spectrometer. Here, it is immediately ionized, which means that it is given a charge. Let's recap what we've just learnt. Firstly, the sample will be vaporized into a gas form. Next, the sample will be put into the mass spectrometer. Next, it will be immediately ionized. Ionization can occur by one of two methods. Firstly, we'll look at electrospray ionization. Electrospray ionization is where a voltage is applied. This will cause each particle to gain a hydrogen ion. This means that the sample is converted into a gas made up of positive ions. Alternatively, ionization can also occur using electron impact ionization. Here, an electron gun is used to fire high-energy electrons at the particles. The electrons will repel a single electron out of each particle. This will cause them to become charged and form 1+ ions. We've now finished the stage of ionization, so we'll move on to looking at acceleration. Next, the positively charged ions found in the sample are accelerated by an electric field. It's important that you remember that acceleration relies on the particles being charged. The acceleration plate is negatively charged on the front to attract ions, and positively charged on the back to repel the ions further down in the mass spectrometer. After acceleration, all the ions will have the same kinetic energy. The velocity of a particle depends on its mass and kinetic energy, so the lightest particles will move faster than the heaviest particles. We'll now recap the stages of acceleration. We know acceleration relies on the particles being charged. There is an acceleration plate which will repel ions that are further down the mass spectrometer. At the end of acceleration, all the particles will have the same kinetic energy. Finally, we will move on to ion drift. In this stage, any electric field is absent, so the ions are not deflected and they just pass through. Lighter ions will drift faster than heavier ions. This is one of the simplest stages of mass spectrometry. There is no electrical field present, so the ions will simply pass through. In the final stage, ions are detected. The lighter ions are detected first, as they have a shorter drift time compared to heavier ions. A mass spectrum is generated using the charged ions. For detection to happen, we need the particles to be charged, which is why ionization is so important. The detector will use an electric field to detect the charged ions and form a graph called a mass spectrum. The lighter ions will be detected first, as they have a shorter drift time compared to heavier ions. This means that we can separate out the ions based on mass, as we've just seen in the diagram. A mass spectrum is generated using the charged ions. This is a recap of what we've just learnt. Here's a quick summary of all 5 stages of time-of-flight mass spectrometry. Firstly, the sample is vaporized into a gas form. Next, the sample is placed inside the mass spectrometer. The gas sample is then immediately ionised. The positively charged ions are accelerated by the electrical field. The negatively charged acceleration plate will attract the positive ions on the back. After this stage, all the ions will have the same kinetic energy. In the next stage, the ions will just drift through. This is the stage known as ion drift. Next, the ions will be detected. Finally, a mass spectrum is generated using the charged ions. It's really useful if you can remember these 8 steps for time-of-flight mass spectrometry. AQA exams may ask you to describe the process in a 6-mark question. The mass spectrum is a graph showing the data obtained from a spectrometer. We'll go through this graph step by step. Firstly, we'll look at the axes. The x-axis will show you the mass-to-charge ratio. The charge is normally +1, so the ratio is simply the mass. Next, we'll look at the y-axis. This will show the relative abundance of ions, given as a percentage. Sometimes, the mass-to-charge ratio is expressed as mz. Again, the charge is normally +1, so the ratio is just the mass. The type of ionisation will change the spectrum slightly. As we've just learnt, there are 2 types of ionisation: electrospray ionisation and electron impact ionisation. Firstly, we'll look at the effects of electron impact ionisation. If electron impact ionisation is used, the mass-to-charge ratio of the peak will equal the relative mass of the isotope. In this instance, we'll be assuming that the relative charge is just 1. This means that we will need to know the mass of the isotope in order to work out the mass-to-charge ratio. If we're using electrospray ionisation, the mass-to-charge ratio of each peak is 1 unit greater than the relative mass. This is because a H+ ion is added to each particle, making the mass number increase. This means that we also need to know the mass of the proton in order for us to calculate the mass-to-charge ratio. There are a few key things on a mass spectrometer that will help you determine the isotopic abundance of an element. On the mass spectrum, each line will represent a particle of different mass. Here, there are 2 lines, or peaks. This means that we have 2 different isotopes. Since each isotope is a different mass, this means that each line will represent a particle with a different mass. For example, here we have 2 particles. One of them has a mass-to-charge ratio of 10, whilst the other has a mass-to-charge ratio of 11. If you were looking at a chlorine sample, each peak will represent a different isotope of chlorine. For example, you may see a peak at 35 and at 37. This will represent the 2 isotopes, chlorine 35 and chlorine 37. Here on the mass spectrum we can see 2 lines. The first one is at 35 and the second one is at 37. Some elements have 1 stable isotope. This means we only see 1 peak at the element's relative atomic mass. The height of each peak will give the relative isotopic abundance. The higher the peak, the more abundant the specific isotope is, relative to other isotopes. Here, we can see that the peak number 35 is a lot higher than peak number 37. This means that chlorine 35 is the more abundant isotope compared to chlorine 37. Relative atomic mass can be calculated in two ways. Here, we can see we can either use the percentage abundance or the unit abundance. If we're using the percentage abundance, there are two steps. Firstly, we must multiply the relative isotopic abundance on the y-axis by the mass-to-charge ratio on the x-axis for each isotope to get the total mass. Next, we have to add up the total masses of each isotope, and then divide by 100. We'll have a go with this example. Pause the video now to see if you can figure out the answer. The correct answer is 10.78. We'll see how to work through this calculation step by step. In our first step, we need to find the mass of each isotope of boron. This means we need to multiply the relative isotopic abundance on the y-axis by the mass-to-charge ratio on the x-axis in order to get the total mass. So we saw on the last diagram that we had two peaks, which would represent two isotopes. One of these was boron 10, which was 22%. The other was boron 11. This was 78%. Now we'll do 22 times 10 to give us 220, and we'll also do 78 times 11, which will give us 858. Now we need to add up the total masses of each isotope and divide by 100. This means that we simply have to do 220 plus 858 and divide that by 100. This gives us an answer of 10.78. The relative atomic mass value should be in between the value of the two isotopes and should be closer to the mass of the more abundant isotope. In this case, it was boron 11. This is a good check to do at the end of the calculation. Sometimes the relative abundance on the y-axis is not given as a percentage, but just as a numerical value. When the relative abundance is in percentages, we know that they all add up to 100, hence we would divide by 100. Instead, we'll have to divide by the total sum of the relative abundances. We'll now have a go at the practice question. The important thing to notice here is that the relative abundance is not given as a percentage. So instead of dividing by 100, we would have to divide by the sum of the abundances. So here, we know that boron 10 is 33, and boron 11 was 117. This means that the mass of boron 10 would be 33 times 10, which is 330, and the mass of boron 11 would be 117 times 11, which is 1287. Now we have to add up the total mass of each isotope and divide by the total number of isotopes present. So in our case, we would be adding 330 to 1287, and we'd divide that whole thing by 150. This gives us an answer of 308.58. Mass spectrums can be used to identify elements, since each element has its own distinct mass spectrum. When we see a mass spectrum with peaks at 35 and 37, we'll know that it's chlorine. Some elements are diatomic. For example, chlorine is normally present as Cl2. In the mass spectrometer, the chlorine atoms will become ionized to form molecular ions. These ions are quite unstable, so will often split up to give chloride ions. Therefore, the mass spectrum has a mixture of chlorine molecules and chlorine atoms. However, we must remember that chlorine has two isotopes, Cl35 and Cl37. This will lead to a huge range of peaks. We can see several of these peaks here. We'll explore each of these in more depth. Firstly, we saw a peak at 70. This is the chlorine molecular ion, made up of two chloride 35s. The peak at 72 is made up of a Cl35 and a Cl37. The peak at 74 is made up of two Cl37s. The peak at 35 is simply the Cl35 ion, whilst the peak at 37 is a Cl37 ion. You should be able to work out each of these by simply adding up the numbers. For example, 70 would just simply be 35 plus 35. The 72 would be 35 plus 37. Mass spectrums can identify molecular samples as well. We touched slightly on molecules when we discussed diatomic elements. Let's consider the mass spectrum of CO2. It enters the mass spectrometer and is ionized to the molecular ion CO2+. This is very, very unstable. This means that it gets broken down into many different fragments. And the final sample detected in the mass spectrometer is made up of all the molecules shown here. This leads to many peaks being produced on the mass spectrometer. If we look at the peak furthest to the right, which is also called the molecular ion peak, we should be able to determine the relative molecular mass of the particle. The peaks furthest to the left are caused by fragments of the particles, which we mentioned earlier.